Hello there and welcome to the Sleepy Universe story. I'm so glad you've joined me tonight. Tonight's journey takes us into the hearts of the saint. Ours, the great engines of the universe. These glowing spheres of fire are more than just distant points of light. Some are so large they could swallow our entire solar system. Others collapse into tiny remnants that spin hundreds of times a second, and every one of them is a forge creating the elements that make up our bodies, our world, and everything we know. When we look at the night sky, we are really looking back in time. The starlight reaching our eyes tonight may have left its source hundreds, thousands, or even millions of years ago. Some of those stars may already be gone. They're like the only whisper of what once was. Yet others will continue to shine long after our world has passed. If you enjoy these gentle journeys, consider liking and subscribing more. Share your thoughts in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, you don't need to do anything at all. Just settle in, let your breathing slow, and allow your thoughts to drift a little lighter. If you're ready, let's begin. The largest known stars would swallow Earth's orbit whole. Some stars are so large that their sheer scale defies imagination. The red hypergiant UI, for example, has a radius more than 1,700 times that of the Sun. If placed at the center of our solar system, its outer surface would stretch beyond the orbit of Jupiter. Even smaller supergiants, like Betelgeuse or Vicenus Majoris, would completely engulf the orbit of Earth. These massive stars are relatively rare, burning through their fuel key supply and living only a few million years. Compared to the billions enjoyed by ordinary stars, their swollen atmospheres are unstable, shedding material into space in great clouds that drift outward. Like smoke. The sheer size of these giants reminds us that our own sun, though immense by everyday standards, is modest compared to the truly colossal suns scattered throughout the galaxy. Some stars burn hot enough to outshine entire galaxies, while most stars shine with familiar brilliance. Certain rare titans called quasars and hyperluminous stars can pour out more energy than the combined light of billions of suns. Stars like Eta Carinae, a luminous blue variable, release so much energy that they rival the brightness of entire small galaxies. For a time in the 19th century, Eta erupted so violently that it briefly became the second brightest star in the night sky. Even though it lies more than 7,000 light-years away, stars of this type live dangerous, consuming their hydrogen at astonishing rates and often ending in explosive supernovae. Their immense light pushes outward so strongly that it blows away their outer layers in powerful winds, creating glowing nebulae that surround them. These beacons of brilliance remind us that even a single star can for a short time dominate the cosmos around it. Neutron stars are the remains of stellar explosions. When a massive star ends its life in a supernovae, its core may collapse into something extraordinary, a neutron star. These objects are only about 20 kilometers wide, yet contain more mass than the Sun. The collapse squeezes atoms so tightly that protons and electrons merge into neutrons, creating matter denser than anything else known outside of black holes. A single teaspoon of neutron star material would weigh billions of tons. Their surfaces are solid, their gravity immense, and their magnetic fields unimaginably strong. Despite their tiny size, they shine across the sea, osmos by emitting beams of radiation or by heating their surroundings with leftover energy. Neutron stars are stellar ghosts, the collapsed cores of once great suns now transformed into spinning, dense remnants that challenge our understanding of matter. They show us the astonishing extremes to which the universe can push the laws of physics. Pulsars spin hundreds of times per second. Among neutron stars, some take on an even more astonishing behavior, known as pulsars. They rotate at staggering speeds, often hundreds of times per second. With each spin, they sweep beams of radio waves or light across space, creating a regular pulse as seen from Earth. The fastest pulsars, called millisecond pulsars, can spin more than 700 times every second, faster than the blades of a kitchen blender. These pulses are so precise that astronomers use them as cosmic clocks, timing them with better accuracy than atomic standards. The discovery of pulsars in the late 1960s even raised speculation that they could be signals from extraterrestrial civilizations before their true nature was revealed. Today, pulsars are used to test the predictions of Einstein's theory of relativity and even to search for gravitational waves rippling across the universe. They are among the most reliable lighthouses in the cosmos. Magnetars have magnetic fields strong enough to all rip atoms apart. Magnetars are an exotic type of neutron star defined by their magnetic fields, the strongest known in the universe. A magnetar's field can be up to 1,000 trillion T, and stronger than Earth's. Such power is almost impossible to grasp. It would be enough to distort atomic structures, tearing apart molecules and rearranging matter itself. When their magnetic fields if suddenly, magnetars can unleash giant flares, releasing more energy in a fraction of a second than the sun emits in hundreds of thousands of years. These bursts have been detected across vast distances, sometimes briefly outshining every star in our galaxy combined. Fortunately, magnetars are rare and none are near enough to pose a threat to Earth. They serve as extreme laboratories in space, showing us what happens when physics is pushed beyond limits we can recreate on Earth. Some stars spin so quickly they flatten into oblate shapes. Not all stars are perfect spheres. When a star rotates extremely rapidly, centrifugal force causes its equator to bulge outward, flattening it into an oblate, squash shape. One famous example is the star Enner, which spins so quickly at its diameter at the equator is 50% larger than from pole to pole. Such rapid spinning can fling material into space, forming disks of gas around the star. These distorted suns challenge our image of stars as round, balanced orbs. Instead, they reveal that stellar lives can be dynamic and turbulent, influenced by spin as well as mass and age. Rapidly rotating stars may also mix their internal layers more effectively, prolonging their lifetimes compared to slower rotating siblings. When seen from afar, they sparkle like any other star, yet up close, they are wildly stretched by a relentless pull of their own speed. Hypergiants can lose more mass than the sun every year. Hypergiants are among the most unstable and short-lived stars in the universe. Their immense size comes at a cost. They burn through their fuel so ferociously that their outer layers cannot stay bound. Instead, they shed mass in powerful stellar winds, losing more than the sun's entire mass. In just a few thousand years, ETA, one of the most famous hypergiants, is surrounded by a vast nebula created by material it has blasted into space. These storms of gas and dust enrich the galaxy with elements that can eventually form new stars and planets. But for the hypergiant itself, the process is destructive. Its fate is almost certainly to explode in a violent supernova, perhaps even leaving behind a black hole. These stars are cosmic firestorms, beautiful and destructive, showing the extremes of what a star can be. Stars can be torn apart by black holes. A star that ventures too close to a black hole faces a violent end. The black hole's tidal forces, differences in gravity between the near and far sides of the star stretch it like taffy. If the saint are strays too close, it is torn apart in a cataclysm called a tidal disruption event. The stellar material spirals inward, forming a glowing disk as it falls into the black hole. This process releases a burst of light that can briefly outshine the combined stars of an entire galaxy. Sometimes jets of material are launched outward at near light speed, broadcasting the destruction across the universe. These events are rare, but they provide astronomers with a way to study otherwise invisible black holes. Each one is a cosmic drama, a brilliant star shredded by the ultimate force of gravity. Tidal disruption events rip stars apart in brilliant flares. When astronomers observe sudden intense flares of light at the centers of galaxies, they may be witnessing the destruction of a star by a black hole. These tidal disruption events occur when a star strays within the black hole's gravitational grasp and is stretched beyond recognition. The star's material forms an accretion disk, heating to millions of degrees and shining in X-rays and ultraviolet light. These flowers can last for months or years as the black hole devours its meal, gradually dimming as the star's remnants vanish. Observing these events helps scientists measure the masses of black holes and understand how galaxies evolve. They also serve as powerful reminders that even stars immense, radiant, and enduring are not safe from the deeper forces that shape the universe. To watch one unfold is to glimpse the rock-consuming hunger of gravity itself. Colliding stars can produce gravitational waves. When two stars in a close binary system spiral together, their collision can be one of the most dramatic events in the universe. Neutron stars in particular release energy not only as light but also as ripples in the fabric of spacetime itself. Gravitational waves. These waves travel outward at the speed of light, stretching and squeezing space as they go. In 2017, astronomers detected gravitational waves from such a collision, followed by bursts of gamma rays and visible light. It was the first time humanity observed both gravitational waves and light from the same cosmic event. These collisions also forge heavy elements, like gold and platinum, seeding the universe with the materials that later form planets and life. Every ring of gravitational waves we detect is an message from stars colliding unimaginably far away. Some stars are ejected into intergalactic space. Not every star remains safely in its galaxy. Some are flung outward at such high speeds that they escape entirely, drifting alone through the vast darkness between galaxies. These rogue stars can be launched by violent events, such as a close encounter with a supermassive black hole or the chaotic breakup of a star cluster. Once ejected, they wander the cosmic void carrying their planets, if any survived, into unimaginable isolation. Imagine a lone sun billions of years from its birthplace, traveling endlessly with no galaxy to call home. Though they are hard to detect, astronomers believe there could be countless intergalactic stars scattered like embers blown from a fire. They remind us that space is not static, but full of motion and chance, and that even something as massive as a star can be cast adrift in the cosmic sea. The first stars may have been hundreds of times more massive than the sun. In the early universe, before galaxies took shape, the very first stars were born. Astronomers call their population the third stars, and they were likely enormous, some hundreds of times more massive than our sun. With no heavy elements to cool the clouds of gas they formed from, these giants grew rapidly and burned with ferocious intensity. Their lifespans may have been only a few million years, a brief flash on cosmic time scales. When they died, they exploded in a colossal supernova, seeding the universe with the first carbon, oxygen, and iron, the building blocks for planets and life. None of these primordial stars survive today, but their fingerprints remain in the ancient chemical patterns of the cosmos. By studying those clues, scientists are piecing together the story of how the first light pierced the darkness, transforming the universe from empty hydrogen to a place capable of life. White dwarfs will eventually cool into black dwarfs. When stars like our sun reach the end of their lives, they shed their outer layers and leave behind a hot, dense core called a white dwarf. First, these remnants shine brilliantly, glowing with the leftover heat of their past nuclear fires. But over billions and trillions of years, they slowly radiate away that energy, fading into darkness. The final stage is called a black dwarf, a cold dead star that no longer emits light. None yet exist because the universe itself is not old enough for even the oldest white dwarfs to cool that much. The idea of black dwarfs belongs to the far future, a time when the cosmos will be a quieter, darker place. They represent the ultimate destiny of countless suns, a silent testimony that even the most radiant stars eventually surrender to time. The universe may end in darkness as the last stars die. If the universe continues to expand forever, then its distant future may be a long descent into darkness. Stars will gradually exhaust their fuel, and no new ones will be born. Red dwarfs, the slowest burners, could glow for trillions of years, but even they will eventually fade. Galaxies will grow dim, planets will freeze, and the night sky will be empty of starlight. In this vision, sometimes called heat death, the cosmos becomes cold and quiet, with only black holes and the faint embers of dead stars remaining. Though this future lies unimaginably far away, the thought is both humbling and strangely peaceful. The story of stars has a beginning, and an end, and we are alive at a moment when the sky is still bright with their light. To gaze upward now is to witness a universe still in its vibrant, star-filled youth. Some theories suggest new stars could form in future universes. While our universe may one day fade into darkness, some theories suggest that this is not the end of the story. Ideas from cosmology propose that our cosmos might bounce or give rise to entirely new universes. In those fresh beginnings, the cycle of stars could ignite once more. The elements forged in our universe could seed the next, ensuring continuity across cosmic generations. Just as stars die and scatter the ingredients for new stars to form, universes themselves might undergo a similar rhythm, collapsing, rebirthing, and renewing. Though highly speculative, this concept offers a vision where starlight never truly ceases. Instead, it shifts across scales larger than we can easily imagine. In this view, the stars above are not just part of our universe, but part of a pattern that could repeat endlessly, an eternal dance of light and renewal. The smallest stars can burn for trillions of years. Not all stars live fast and die young. The smallest ones, called red dwarfs, burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. These stars are dim and cool compared to our sun, often invisible to the naked eye from Earth. Yet, they are by far the most common stars in the cosmos, making up the majority of suns in the Milky Way. Because they live so long, red dwarfs could host planets where life has time to emerge and evolve over time scales unimaginable to us. None of them have yet reached old age, since the universe itself is too young. That means the night sky of the far future will still be lit by these tiny, enduring embers long after brighter stars like the sun have vanished. Over trillions of years, only faint red stars will remain. As the cosmos ages, the brightest, most massive stars will burn out first. Blue giants and hypergiants live only millions of years. Stars like the sun last for billions. But red dwarfs, those small efficient stars, endure for trillions. Over immense time scales, they will become the dominant light sources in the universe. The galaxies of the distant future may go only with their faint red light, a softer and lonelier sky. Eventually, even these long-lived stars will run out of fuel, fading into white dwarfs, and at last into black dwarfs. Universe will shift from a bright star-filled expanse to one lit only by fading embers. It's a vision of cosmic twilight where the last stars burn quietly, carrying the universe into its final chapters. For now, we live in its golden age, surrounded by brilliant suns of every size and color. Stars can orbit close to supermassive black holes. At the centers of galaxies lurk supermassive black holes, millions to billions of times heavier than the sun. Amazingly, stars can orbit right around them, tracing paths that test the limits of gravity. In our Milky Way, astronomers have observed stars racing around Sagittarius, an asterisk, the black hole at our galactic core. One such star, S2, swings within just 17 light hours of the black hole, a cosmic hair's breadth. At closest approach, it moves at more than 50 kilometers per second. Observing these orbits allows scientists to measure the black hole's mass with extraordinary precision and to confirm Einstein's predictions about how gravity warps spacetime. These stars survive where we might expect them to be torn apart, showing that even in the shadow of a black hole, the dance of starlight can endure. The fastest stars can slingshot away from black holes. When a star strays too close to a black hole, it doesn't always get destroyed. Sometimes it is flung away at tremendous speeds, accelerated by the immense gravity. These hypervelocity stars can travel millions of kilometers per hour, fast enough to escape their home galaxy entirely. The Milky Way contains several such runaway stars, racing outward into intergalactic space. Their journeys may have begun near Sagittarius asterisk, where interactions with the central black hole acted like a slingshot. For any planets that might orbit such a star, the result would be extraordinary. A solar system cast adrift, speeding alone through the cosmic dark. The discovery of these stellar exiles reveals how dynamic galaxies see and be, and how black holes shape not only what falls in, but also what gets hurled away. Many of the stars you see are actually multiple systems. To the naked eye, a star often appears as a single point of light, but in reality, many are doubles, triples, or even larger groups bound by gravity. Binary stars are especially common, with two suns orbiting a shared center of mass. Some pairs are so close that they exchange material, while others are so far apart they circle each other only once every thousands of years. To an observer on a planet orbiting such a system, sky might feature 2 or 3 suns rising and setting, together casting multiple shadows. Famous examples include Alpha Centauri, our nearest stellar neighbor, which is a triple system. By studying these pairs and groups, astronomers gain insight into how stars form and evolve. What looks like a solitary light in the night sky is often a hidden family orbiting together in a long, graceful dance. The death of a star can trigger the birth of new ones. When a massive star ends its life in a supernovae, it doesn't just disappear, it reshapes its surroundings. The explosion blasts shockwaves into nearby clouds of gas and dust, compressing them and triggering new waves of star formation. In this way, the death of one star can set off the birth of many others, our own and may have been born from such an event. Its nebula enriched by heavy elements scattered by a previous generation of giants. These cycles ensure that galaxies remain fertile with starlight, continually recycling matter into new forms. Every brilliant star that dies leaves behind more than ashes. It leaves the seeds of future suns, planets, and perhaps life itself. Stars don't simply end, they pass the torch, igniting the next chapters in the ongoing story of the cosmos. Some stars explode more than once in rare supernovae rebounds, while most stars that explode as supernovae end in finality. A few defy expectations. In extremely rare cases, a massive star may erupt violently, survive the blast, and then explode again years or decades later. These unusual events are called pulsational perturbability supernovae. The star becomes unstable, ejects huge amounts of mass, then stabilizes temporarily, only to later collapse for good. Such stars shine unpredictably, producing multiple bright outbursts that can confuse astronomers into thinking they're witnessing repeated supernovae in the same place. These exotic stellar deaths highlight how diverse the fates of massive stars can be and how much we still have to learn about the limits of nuclear fusion and instability. In cosmic terms, they are stars that seem unwilling to let go, leaving a dramatic flickering record of their struggle against gravity's final pull. Type E supernovae help us measure the size of the universe. Type Ia supernovae are a special class of exploding stars that shine with remarkable consistency. They occur when a white dwarf star in AB inner system accumulates too much matter from its companion, igniting in a runaway thermonuclear explosion. Because these explosions always happen at roughly the same critical mass, their peak brightness is nearly uniform across the universe. This makes them standard candles, reliable beacons that astronomers can use to measure cosmic distances. By comparing how bright they appear from Earth to how bright they truly are, scientists can calculate how far away they must be. Type A supernovae played a pivotal role in one of astronomy's greatest discoveries, the accelerati, an expansion of the universe driven by dark energy. They are not only spectacular stellar deaths, but also fundamental yardsticks that help us grasp the immensity of the cosmos itself. Supernovae scatter heavy elements across the galaxy. Every atom of gold, silver, iron, and calcium on Earth was forged in the heart of a star. When massive stars explode as supernovae, they blast those heavy elements into space, enriching the interstellar medium. Over time, that material becomes part of new stars, planets, and living things. Without supernovae, the universe would be a muck. Super place filled mostly with hydrogen and helium. Instead, every explosion sows the seeds of complexity. The iron in your blood and the calcium in your bones were once carried outward and sucked, each a blast, drifting through space before finding their way into Earth. Supernova are violent endings, but they are also beginnings, scattering the ingredients of life far and wide. In this way, stars are both creators and destroyers, ensuring that the universe is filled not only with light, but with richness and variety. You are literally made of stardust. It may sound poetic, but it is scientifically true. The atoms in your body were forged in stars. The oxygen you breathe, the carbon forming your cells, the iron in your blood, all were created in stellar cores and supernovae billions of years ago, before Earth even existed. Those elements were drifting in space, awaiting their chance to come together. Carl Schwann famously said, "We are made of star stuff." And the phrase captures a profound reality. Every human being, every tree, every stone is a collection of recycled stardust. When you look up at the night sky, you are not just gazing at distant suns. You are seeing your own origins. The stars gave us the raw materials, and in turn, we are the universe becoming aware of itself. The link between us and the stars is direct, literal, and deeply humbling. Iron marks the point where fusion can no longer power stars shine because of nuclear fusion, the process of fusing lighter elements into heavier ones. This process releases energy, but only up to a point. When a star's core begins to fuse silicon into iron, the balance changes. Iron does not release energy when fused. Instead, it absorbs it. This means that once iron accumulates in a star's core, fusion can no longer support the star against gravity. At that moment, collapse becomes inevitable, leading to a catastrophic implosion and often a supernovae. The presence of iron is a death sentence for massive stars, marking the moment when their fuel runs out in a fundamental way. It's remarkable that this ordinary metal, so familiar to us on Earth, is also the cosmic tipping point that decides when giants of light will fall. Stars balance gravity with outward pressure from fusion. A star is held together by a delicate balance between two opposing forces. Gravity pulls all of its mass inward, trying to collapse it into a dense core. Fusion, the burning of hydrogen into helium in the center, pushes outward with heat and radiation. As long as these two forces remain in balance, the star is stable. Too much pressure, and it swells. Too little, and it contracts. Our sun has maintained this equilibrium for billions of years, and will continue to do so for billions more. But when the fuel at its center eventually runs out, the balance will tip and the sun will transform into something entirely new. This tug of war is the fundamental reason stars exist as steady sources of light rather than collapsing instantly or blowing themselves apart. Without fusion, stars would collapse instantly. Fusion is not just what makes these stars shine, it is what prevents them from imploding. Without the outward push of energy from fusion, gravity would crush a star into a dense collapsed state in mere moments. Even our sun would. Its gentle yellow glow is balanced on this knife edge every second. The constant fusion of hydrogen into helium keeps it from collapsing under its own immense weight. For larger stars, this balancing act is even more extreme with incredible forces in play. When fusion finally ends, gravity always wins, pulling the star into a white dwarf, neutron star, or black hole. Stars exist only as long as fusion continues. Their light is a fragile victory against the relentless inward pull of gravity. Some stars burn fuel 1,000,000 times faster than the sun. Not all stars are patient like our sun. The most massive ones consume their nuclear fuel at astonishing rates, up to 1,000,000 times faster. This means that although they are much larger and more powerful, they live incredibly short lives, sometimes lasting only a few million years. By contrast, the sun will shine for roughly 10 billion years. These fast-burning giants blaze with blue light, pouring energy into space and shaping their galaxies with radiation and stellar winds. Their short lives end violently, often in supernovae that seed the cosmos with heavy elements. The contrast between them and stars like our sun shows how size dictates destiny. The bigger the star, the shorter and more dramatic its life. They are cosmic fireworks, dazzling but fleeting, while smaller stars remain as steady candles across deep time. The sun will one day expand into a red giant. Our own sun, though stable now, has a dramatic future. In about 5 billion years, it will exhaust the hydrogen in its core as fusion shifts to helium. The balance inside will change and the sun will swell enormously into a red giant. Its surface will expand outward, likely engulfing Mercury and Venus, and perhaps even Earth. The sun's outer layer will glow a dim red, far cooler than today's golden light, while its core contracts and heats up. Eventually, the outer layers will drift away into space, forming a glowing planetary nebula, while the core shrinks into a white G. Though this transformation is far in the future, it is a reminder that even stars like our sun are temporary, following paths written into the fire. 6 of fusion and gravity. Our familiar star will one day become something entirely different. The brightest star in Earth's sky is Sirius. On a clear night, Sirius dominates the heavens, also called the dog star. It shines nearly twice as bright as the next brightest star, Canobus. Part of its brilliance comes from its intrinsic luminosity, but its relative closeness, only about 8.5 light-years away, makes it appear dazzling from Earth. Ancient cultures noticed Sirius for thousands of years, linking it with myth, calendars, and navigation. In ancient Egypt, its rising in the dawn sky heralded the flooding of the Nile. Today, astronomers know Sirius is actually a binary system: the bright Sirius A, a hot white star, and Sirius B, a faint but dense white dwarf, once a massive star itself. To the naked eye, they blend into one piercing point of light. Sirius is not only bright, but a reminder that appearances in the night sky often hide deeper stories. Some stars have names dating back thousands of years. Long before telescopes, people gave names to the brightest stars they could see. These names carried meaning tied to agriculture, navigation. Our myth. Stars like Betelgeuse, Real, and Aldebaran trace their names to Arabic traditions, while Vega and Altair come from ancient Arabic and Latin roots. In China, India, Greece, and Egypt, stars were woven into stories that help civilizations make sense of the sky. Even today, those ancient names endure, connecting us to people who watched the same sky millennia ago. Behind every familiar constellation lies a tapestry of human history with names passed down through languages and cultures. While astronomers now use catalog numbers for precision, the old names remain echo. Across time, they remind us that our bond with the stars isn't just scientific, it's deeply cultural, stretching back to the very beginning of civilization. Ancient cultures used stars to navigate oceans before compasses and GPS. The stars served as reliable guides. Polynesian voyagers crossed the Pacific by memorizing the rising and setting points of stars, steering their canoes across thousands of kilometers of open sea. The North Star, almost fixed in the sky, has long been used in the northern hemisphere to find latitude. Arab traders, Greek sailors, and Viking explorers all relied on the sky map to guide their journeys. Even seasonal migrations of people and animals were often timed by the stars. These skills were passed down orally with songs and stories encoding entire star charts. Navigation by the stars required extraordinary memory and observational skill, but it worked. Long before technology, humans trusted starlight to carry them safely to new lands. Today, the same stars shine above, though we now look to them with wonder rather than necessity. The North Star changes over time. Polaris is famous as the North Star, the one point in the sky that seems to stand still while all the others rotate around it. But it hasn't always held this role, and it won't forever. Earth's axis slowly wobbles in a cycle lasting about 2,600 years, a motion called precession. This means the pole star gradually shifts. Around 3000 BCE, the star Thuban in the constellation Draco marked true north. In about 12,000 years, the bright star Vega will take its place. Alaris is just the current chapter in a long story of shifting skies. Ancient monuments like some pyramids and stone circles were aligned to different stars that once held the northern crown. Watching the pole star changes like watching Earth breathe across millennia, a reminder that even the patterns we trust in the heavens are always moving. Our sky looks different from other worlds. If you could stand on a distant planet, the constellations, would vanish. Stars appear grouped together from Earth only because of our particular vantage point. Seen from IQ's away, their arrangements would warp into unfamiliar patterns. On a planet orbiting Proxima Centauri, our sun would appear as a faint additional star in the sky from Andromeda. The Milky Way itself would be seen as a glowing band, while the stars we hold familiar would be lost in its swirl. This shifting of perspective shows that constellations are illusions of distance and angle. The night sky is not a fixed picture, but a three-dimensional ocean of suns appearing differently from every shore. To imagine other skies is to realize how deeply our view of the universe is shaped by where we stand within it. Future civilizations will see entirely new constellations. The constellations we know, Orion, Cassiopeia, the Big Dipper, are temporary. Over thousands of millions of years, stars drift through space, moving relative to one another. Slowly, the familiar patterns will warp beyond recognition. The hunter Orion may lose his belt, the Dipper why lose its handle, and entirely new groupings will emerge to us. These changes are too slow to notice in a lifetime, but on cosmic scales, the sky is ever-changing. Future civilizations or even future species will inherit skies filled with different maps. The mythology of their constellations will be unique to their time, just as ours are tied to ancient cultures. The constellations we see tonight are snapshots of a fleeting arrangement, a reminder that nothing in the cosmos is permanent, not even the patterns we draw in the stars. The light of stars can be distorted by gravitation. Lensing. Gravity bends light, a prediction made by Einstein and confirmed a century ago. When the light of a distant star passes near a massive object such as a galaxy or black hole, it can be bent and magnified. This phenomenon is called gravitational lensing. Sometimes it can split a star's light into multiple images or make it appear far brighter than it really is. Astronomers have then observed individual stars magnified this way, briefly visible across billions of light years. Without lensing, those stars would be impossible to detect. Nature's magnifying glass allows us to peer farther into the universe than our instruments alone could manage. It shows us that space is not empty but flexible, bending light in ways that reveal hidden treasures. Even the path of starlight is shaped by the invisible hand of gravity. Some constellations will disappear in the far future. Constellations are cultural creations, patterns traced on the backdrop of the stars, but they are not eternal. As the Milky Way rotates and stars drift, some of today's most recognizable shapes will vanish. In about 50,000 years, Orion will lose its familiar form, its bright stars scattering across the sky. In a few million years, the Big Dipper will no longer look like a dipper at all. To future observers, these constellations may not exist in any recognizable way, just as ancient humans saw different skies than we do. Future beings will inherit their own. The constellations we know are simply temporary alignments, and our myths are tied to a passing arrangement of stars. They remind us that the sky itself has a history, and the maps we make of it will someday be as outdated as old charts of the seas. The positions of stars slowly shift over millennia. They appear fixed. Stars are constantly moving. Their immense distances make the motion nearly invisible to the naked eye, but over centuries and millennia, the changes add up. This gradual drift is called proper motion. Barnard's star, for example, shifts noticeably against the background every few decades, the fastest known proper motion of any star in the sky. Ancient star maps compared to modern ones reveal the slow shuffle of the heavens. Even the shapes of constellations change subtly over human history. This shifting sky reminds us that what seems eternal is not. The stars are not pi-headed dots on the dome. They are suns traveling through the galaxy with their own paths and stories. They're like tracing lines of motion across cosmic time. The sun once had different neighboring stars. Our sun doesn't remain fixed in place either. It orbits the center of the Milky Way every 200 million years. Along the way, its neighborhood changes. Stars that are near us today will drift away, replaced by others crossing our galactic path. In the distant past, the sun's closest neighbors were entirely different. Their light mingled with ours in a different sky. As it continues its journey, the constellations around us will transform, and the stars we know will fade from view. This cosmic motion shows that even our sun's place is temporary, part of a grand rotation, carrying us around the galaxy. To look at the sky is to see just one frame of an endless journey where our stars' companions come and go across the ages. Globular clusters contain some of the oldest stars in the universe. Globular clusters are dense, spherical swarms of stars, often containing hundreds of thousands packed into a relatively small space. They orbit the outskirts of galaxies like glittering satellites, each one a fossil of the early universe. Many globular clusters in the Milky Way are more than 12 billion years old, nearly as ancient as the universe itself. Their stars are generally small, faint red dwarfs, and long-lived giants. While massive stars burned out eons ago, viewed through a telescope, a globular cluster looks like a dazzling snowball of light with stars roding so tightly in the center that they blur together. These clusters are more than beautiful. They're windows into the past, showing us how the first stars formed and lived. Studying them is like reading a history book written in starlight, tracing the early days of our galaxy. Some ancient stars in the Milky Way are nearly as old as the universe. Hidden among the younger generations of stars in our galaxy are a few elders, ancient suns that date back almost to the dawn of time. Some are more than 13 billion years old. nearly as old as the universe itself. These SDA was formed from primordial gas containing very few heavy elements. Astronomers identify them by studying their spectra, the fingerprints of elements in their light, and finding signatures almost untouched since the Big Bang. Such ancient stars are rare, but they offer clues about the first moments of star formation before galaxies matured and heavy elements filled the cosmos. To gaze upon one is to look into deep time, connecting with a survivor from an era when the universe was still young and dark, just beginning to sparkle with the first starlight. Stars can outlive the galaxies that formed them. Galaxies are dynamic, sometimes colliding, merging, or even being torn apart by gravitational forces. Yet, stars within them can outlast these transformations. A star born in a small galaxy might find itself swept into a larger one after a galactic merger, continuing to shine for billions of years. Some stars may even be flung into intergalactic space, wandering alone long after their whole galaxy has dissolved. In this way, stars can survive events that erase the very structures that created them. It's a reminder that stars are both products of galaxies and independent entities, carrying on long after galactic boundaries shift. These lone survivors are cosmic witnesses living through upheavals on scales almost too vast to imagine, their light outlasting the cradle as that first ignited them. Some stars are surrounded by mysterious shells of gas. Not all stars shine in isolation. Some are cloaked in strange shells of gas and dust ejected from their surfaces during periods of instability. These shells can form glowing rings, arcs, or bubbles lit up by the star's radiation. The reasons vary. Some stars lose mass through strong stellar winds, while others undergo eruptions that briefly swell and shed their outer layers. Often, the material becomes part of an intricate nebula, creating beautiful and sometimes puzzling patterns. In some cases, astronomers see multiple shells, suggesting a star has undergone repeated episodes of shedding. These gas shells don't just decorate the stars, they enrich the galaxy with elements that will one day form new stars and planets. To study them is to catch a star in the act of change mid-transformation, wearing its history in glowing veils. Wolf-Rayet stars shed neon powerful winds. Wolf-Rayet stars are rare, massive, and incredibly unstable. They burn so hot and bright that their outer layers are blown away in fierce stellar winds. These winds can strip away more than 10 Earth masses of material every year, creating dramatic halos of gas and dust around the star. Their exposed cores glow with searing heat, often reaching temperatures above 50,000 C. Wolf-Rayet stars are considered to be in a transitional stage, living short, violent lives before exploding as supernovae or collapsing into black holes. Despite their rarity, they play an outsized role in enriching galaxies with heavy elements. Their turbulent winds and eventual explosions scatter the raw ingredients for new worlds. They are stars living on the edge, burning so intensely that they cannot last long, blazing fiercely before their inevitable end. Some stars create bow shocks like boats in water. When a star races through space at high speeds, it can plow into surrounding gas and dust, creating a bow-shaped shock wave in front of it, much like the wake of a boat moving through water. These bow shocks glow in infrared light, where astronomers can spot them as arcs or crescents ahead of the star. They reveal both the motion of the star and the density of the medium it is passing through. Such stars are often runaways, ejected from their birthplaces by explosions or gravitational encounters. Their glowing wakes are fleeting, lasting only while the star speeds through gas-rich regions. Each bow shock is like a frozen wave in space, a luminous footprint marking a star's restless journey across the galaxy. Runaway stars race through space at incredible speeds. Not all stars remain tethered to their birthplaces. Some are ejected from their clusters or galaxies at speeds reaching hundreds of kilometers per second. These runaway stars can be launched by supernovae explosions that kick them away or by close encounters with massive black holes. In extreme cases, they achieve hypervelocity fast enough to escape their galaxy entirely. For any planets orbiting such a star, the result would be extraordinary. A solar system hurled alone into the cosmic wilderness. Though rare, runaway stars show the chaotic side of the universe where stellar lives can be suddenly uprooted by violent forces. They streak across the galaxy like cosmic exiles, reminders that even stars are not immune to the unpredictability of gravity's games. The youngest stars are often hidden behind dust. Newborn stars rarely reveal themselves right away. They are born in thick clouds of gas and dust, the remnants of the material that collapsed to form them. These dusty cocoons block visible light, hiding the stars from ordinary telescopes. Instead, astronomers use infrared and radio observations to peer through the veil, revealing clusters of protostars still gathering mass. Often, these young stars are surrounded by disks of material that may one day form planets. In time, radiation and stellar winds clear away the dew. Saint, and the stars emerge, shining freely. To catch a glimpse of a newborn star is to witness creation in progress, a rare and delicate stage that lasts only a fraction of a star's life. Protostars glow before nuclear fusion even begins. A star doesn't begin its life by immediately igniting fusion. Before that moment, it exists as a protostar, a dense clump of gas collapsing under gravity. As it contracts, the core heats up, and the protostar glows faintly from gravitational energy alone. During this stage, which can last hundreds of thousands of years, the star gathers material from its surroundings, growing larger and hoofer. Jets of gas often stream from its poles, marking its presence in the dark clouds where it forms. Only when the core temperature reaches about 10 meters, does hydrogen fusion begin, and the protostar officially becomes a star. This hidden phase is the universe's quiet prelude to starlight, when the future of a sun is still being assembled. From darkness, brown dwarfs blur the line between planets and stars. Not all objects in space neatly fit the definition of a star or a planet. Brown dwarfs occupy the twilight zone between the two, too massive to be called planets, but not massive enough to sustain steady hydrogen fusion like true stars. They glow faintly with leftover heat from their formation. Some briefly fuse deuterium, a heavy form of hydrogen, before fading into dim, cool objects. Brown dwarfs can be hard to spot, shining mostly in infrared light, but astronomers have found many of them drifting alone or orbiting stars. They demonstrate the diversity of objects the universe can create, challenging our categories. In a sense, they are failed stars or perhaps overgrown planets, reminding us that the cosmos often resists simple energy, sometimes producing spectacular outbursts visible across the galaxy. When they merge, the stars often become larger, hotter, and more unstable, with new layers of nuclear fusion igniting in their cores. Some mergers may even create rare types of stars that could not form naturally otherwise, like boostreggers, stars that appear unusually young because they have been rejuvenated by merging. These events can also leave behind disks of material that may shape new planets or simply scatter into space. Though violent stellar mergers are a part of the cosmic cycle, reshaping stars into new forms, they remind us that the lives of stars are not isolated, but interconnected, influenced by neighbors and chance encounters. Binary stars can steal mass from one another. In many binary systems, one star grows at the expense of its companion. As stars age and expand into giants, their outer layers can spill over to the other star, pulled by gravity. This mass transfer can dramatically alter both stars' destinies. The receiving star may grow hotter and brighter, while the donor is stripped to its core, sometimes leaving behind a white dwarf. In extreme cases, The stolen mass can push a star over the limit for stability, leading to a nova or even a supernovae. These interactions create some of the most dramatic phenomena in the sky, from flickering variable stars to powerful explosions. Binary stars are cosmic thieves and victims, their lives bound together in relationships as complex and dramatic as any myth, except played out in light and fire across millions of years. Triple star systems can create strange orbital paths. Some stars don't just come in pairs, they form trios orbiting in delicate gravitational dances. Triple star systems can arrange themselves in several ways to close stars with a third orbiting farther out, or all three bound in complex shifting patterns. These systems can create chaotic gravitational effects influencing the motion of any planets that orbit them. In some cases, planets can end up on wildly tilted orbits, experiencing multiple suns rising and setting. Triple systems are relatively common, showing that the universe loves variety. To see one through a telescope is to glimpse an alien solar system very different from our own, where the rhythms of daylight and night would be entirely unlike anything on Earth. Such stars reveal that the ordinary solar system we live in is just one possibility and many strange cosmic arrangements. Planets can orbit multiple stars at once. Science fiction often imagines worlds with two suns in their skies, but astronomy confirms they are real. Planets can orbit binary stars in stable paths, circling both suns together. In such systems, the planet would experience complex cycles with twin sunsets and shifting patterns of light. Other planets orbit only one star in a binary, with the companion star rising and setting like an unusually bright moon. NASA has discovered several such circumlunar planets with the Kepler telescope, proving these exotic arrangements exist. Life under multiple suns would be shaped by cycles unlike anything on Earth. Seasons, light levels, and even shadows could behave unpredictably. These systems expand our understanding of what is possible, reminding us that the diversity of planetary environments is wider than our imagination once allowed. Star clusters can host hundreds of thousands of suns. Not all stars are scattered evenly through galaxies. Some are born in enormous groups. Star clusters can host hundreds of thousands of suns packed tightly into a relatively small region of space. Globular clusters, for example, are so dense that stars in their centers may be only a fraction of a light year apart. In such environments, stars frequently interact, exchanging companions or disturbing planetary systems. Open clusters, looser and younger, often shine with hot, bright blue stars, their short lives highlighting the youth of the group. To look at a cluster through a telescope is to see an entire community of stars shining together, a reminder that many suns begin their lives not in isolation, but in crowded stellar nurseries. Over time, clusters slowly disperse, their members drifting off to join the galaxy at large. Some clusters are billions of years old, while open clusters dissolve within a few 100 million years. Globular clusters endure. Many are more than 10 billion years old, making them nearly as ancient as the Milky Way itself. Their longevity comes from their dense structure, with gravity binding their hundreds of thousands of stars tightly together. Over eons, the brightest stars die, leaving behind red giants and dense remnants, while dim red dwarfs continue shining steadily. These clusters orbit the galaxy like relics, survivors from a time when the Milky Way was still forming. Studying them reveals clues about the earliest conditions of galaxy building as well as the chemical makeup of ancient stars. They are cosmic time capsules preserving information about an era otherwise long gone. Looking at a globular cluster is like looking back across nearly the entire history of the universe. Open clusters slowly dissolve into the galaxy. Open clusters, unlike their globular cousins, are relatively fragile. They form as groups of dozens to thousands of young stars, often within vast stellar nurseries. Over hundreds of millions of years, gravitational tugs from the galaxy gradually pull them apart. Eventually, the stars disperse into the galactic disk, joining the general populace. Our own sun is thought to have formed in an open cluster about 4.5 billion years ago, long since dissolved. Though temporary open clusters provide a snapshot of stellar youth filled with hot, massive stars that illuminate the surrounding gas in brilliant colors, they show that stars are not born alone, but as siblings, companions for a while before scattering into the galaxy to live out their separate fates. Starburst galaxies can spawn stars at furious rates, while galaxies like the Milky Way form stars at a steady pace. Some galaxies undergo bursts of creation so intense that why are called as starbursts. In these environments, stars are born at rates up to 1,000 times greater than normal. Whole regions blaze with newborn clusters. They combine light pouring out like cosmic fireworks. Starbursts can be triggered by galactic collisions where tidal forces compress vast amounts of gas into new stars. Though spectacular, these phases are short-lived on cosmic scales, lasting only tens of millions of years. Eventually, the galaxy exhausts its gas, and the starburst fades. These galaxies show us that the universe's rhythms can vary wildly. Sometimes calm, sometimes explosive, but always creative. They remind us that galaxies are not static collections of stars, but evolving dynamic systems. Stellar nurseries can stretch across hundreds of light-years. Stars are born in giant molecular clouds, vast reservoirs of gas and dust that can span hundreds of light-years. Within these regions, gravity slowly pulls material into clumps that collapse into protostars. Telescopes reveal these nurseries as glowing nebulas where young stars shine against the clouds that birth them. Orion Nebula, visible even to the naked eye, is one of the nearest examples, filled with hot, massive stars, illuminating their surroundings. Inside such nurseries, whole generations of stars can form together, creating clusters that later disperse. To peer into a stellar nursery is to watch creation at work. The raw ingredients of the universe assembling into suns that may one day light planets and even life. These clouds are the wands of the cosmos, shaping the future skies of galaxies. Young stars often blast jets into space. As new stars grow from collapsing gas, many unleash narrow jets of material from their poles. These stellar jets can stretch for light years, plowing into the surrounding clouds and carving luminous trails. The process is thought to help regulate how the star gathers material, channeling excess energy outward while the rest of the gas falls inward. Observed with powerful telescopes, these jets appear as delicate filaments glowing in pinks and blues, lit by shock waves, as they call it, with nearby gas, known as herbage haro objects. They are among the most beautiful sights in astronomy, vivid markers of stellar youth, though they last only a few tens of thousands of years, as they capture the drama of star birth, a brief but extraordinary stage before the star settles into long-term stability. Some stars pulse in brightness with cosmic heartbeats. Certain stars shine with steady light. Instead, they pulse rhythmically, brightening and dimming. These pulsating variable stars expand and contract in cycles driven by changes in pressure and temperature. In their outer layers, some like Shepherd variables are so regular that they act as cosmic clocks with periods tied directly to their intrinsic brightness. By measuring their pulses, astronomers can calculate their true luminosity and use them as distance markers across the universe. Others, like early stars, pulse more rapidly but serve a similar role in mapping the galaxy up to the naked eye. These stars may appear to shimmer oddly, but with careful observation, their beating hearts reveal themselves. Their steady rhythms echo through space, turning stars into natural timekeepers and helping us chart the vastness of the cosmos. White stars burn hotter than blue flames. We often think of fire as the hottest thing we know, But stars outshine even our hottest flames. White stars such as Sirius irradiate at temperatures of 10°C or more, far hotter than the bluish flame of burning gas here on Earth. Their surfaces blaze so intensely that they emit light across a wide spectrum, appearing dazzling white or bluish white. To our eyes, these stars are usually more massive and younger than the Sun, consuming their hydrogen fuel more rapidly. Their brilliance makes them easy to spot in the night sky. Yet, their lifespans are relatively short compared to cooler stars. When we see a white star shining down on us, we're witnessing energy on a scale of early beyond earthly fire, a fusion furnace so hot that even the concept of flame seems small in comparison. Red supergiants are among the coolest but largest stars, despite their fiery color. Red supergiants are surprisingly cool by stellar standards. Their surfaces can be only 3,000 C cooler than our Sun's 6,000, but what they lack in temperature, they make up for in size. Stars like Betelgeuse swell to hundreds or even over 1,000 times the radius of the Sun. Their vast atmospheres puffed out into space. If Betelgeuse sat at the center of our solar system, it would extend past the orbit of Mars. These stars are nearing the ends of their lives, swollen giants preparing for eventual supernovae. Their red glow in the night sky is a signal of both greatness, fragility. Though cooler on the surface, they burn ferociously within, shaping their final destiny as some of the most spectacular stellar explosions in the universe. Yellow stars like the Sun are actually quite ordinary. Some feels central and unique to us, but in the grand scheme of the cosmos, it's an ordinary middleweight star, classified as a yellow dwarf or GTP main sequence star. It burns steadily, neither especially massive nor especially dim. Billions of stars like the Sun dot the Milky Way, each one capable of hosting planets. The Sun's ordinariness is its gift, massive enough to ignite fusion for billions of years, but not so large that it burns out too quickly. It provides a stable, long-term home for life to emerge and evolve. When we look up at the stars, it's comforting to know that our own Sun is not unusual. If life exists elsewhere in the galaxy, it may well orbit a star much like ours, steady, yellow, and reliable. Ordinary in this case, it may be exactly what makes it extraordinary. The most common stars in the universe are red dwarfs. Though they are faint and difficult to see with the naked eye, red dwarfs are by far the most common stars in the universe. Small, cool, and efficient, they make up perhaps 3/4 of all stars in the Milky Way. Their dim red light means none are visible from Earth without telescopes. Despite their abundance, because they burn their hydrogen so slowly, red dwarfs live for trillions of years, much longer than the current age of the universe. This longevity makes them fascinating candidates for hosting habitable worlds, since planets around them would have more than enough time for life to develop. They are the quiet workhorses of the cosmos, far outnumbering the bright blue giants that grab our attention. The galaxy's glittering fabric is mostly woven from these tiny, enduring suns. The rarest stars are the most massive blue giants. At the opposite end of the scale from red dwarfs are blue giants. Stars are dozens of times more massive than the Sun. They burn so fiercely that their lifespans last only a few million years, vanishing in the bowl ink of a cosmic eye. Their rarity comes from this brevity. Though many may form, they die quickly, leaving only a few scattered across the galaxy at any given time. When alive, they blaze with incredible brilliance, often visible across vast distances. Their ultraviolet radiation shapes entire regions of space, ionizing gas clouds and carving out bubbles in the interstellar medium. These stars are the fireworks of the universe, spectacular, short-lived, and impossible to ignore. To glimpse a blue giant is to catch a rare, fleeting phenomenon, a cosmic titan that will soon collapse in one of the most dramatic deaths imaginable. Stars come in colors that human eye can barely see. Stars don't just shine white or yellow. Their light spans a spectrum of colors from deep crimson to icy blue depending on surface temperature. Some stars radiate in shades so subtle that our eyes cannot fully perceive them. To us, they may all appear bluish or whitish, but rough scientific instruments, their colors become clear. Ultraviolet stars blaze with energies our eyes can't detect, while cooler stars glow in infrared, invisible without special sensors. Astronomers met these colors using spectroscopy, splitting starlight into rainbows that reveal its temperature, composition, and motion. In truth, the night sky is far more colorful than it looks, painted in hues just beyond human vision. The stars we see are only a glimpse of a much richer palette, hidden from us, but blazing across the universe in light of every kind of star. As color reveals its temperature, color isn't just decoration. It's a thermometer for stars. The bluer the star, the hotter its surface. Blue giants can burn at tens of thousands of degrees while our red dwarfs glow at only a few thousand. Yellow stars like our sun fall in between. This relationship, known as Wien's law, allows astronomers to estimate stellar temperatures just by studying each. Our light telescopes equipped with filters can measure the balance of colors, giving precise readings. The rainbow spread of starlight also reveals details about a star's composition, motion, and age. Every star is a story written in its color, a direct translation of heat into hue. The next time you see a faint red glow or a sharp white sparkle, remember, you are looking at a thermometer, are written in starlight, a cosmic code that astronomers have learned to read. Low-Mars stars burn fuel slowly and efficiently. Stars come in a wide range of masses, and the smallest ones live the longest. Low-mass stars sip their hydrogen slowly, converting it into helium with remarkable efficiency, unlike massive stars, which blaze through their fuel in a few million years. These smaller suns can shine for trillions of years without exhausting themselves. Their cooler temperatures make them dim, often invisible to the naked eye from Earth, yet they dominate the stellar population of the galaxy. These stars rarely die in dramatic explosions. Instead, they fade gently into white dwarfs, ending their lives quietly. Their longevity and stability make them fascinating targets in the search for habitable planets. Though unimpressive in brightness, low-mass stars are the patient guardians of time, shining long after brighter stars have burned out. Heavier elements, like carbon and oxygen, are forged in stars. The universe began with only the simplest elements: hydrogen, helium, and traces of lithium. Everything heavier, carbon, oxygen, nitrogen, silicon, iron, and beyond, was created in stars. In their cores, nuclear fusion fuses lighter atoms into heavier ones, building the chemistry of life atom by atom. When stars die, they scatter those elements into space, where they are incorporated into new stars, planets, and living beings. The oxygen in your lungs and the carbon in your cells were born in stellar furnaces billions of years ago. Without stars, there would be no rocks, no oceans, no DNA. Each element heavier than helium carries the signature of a star that lived and died before us. To study the periodic table is to read the history of starlight written into the matter of everything that exists. Some stars survive near-death encounters with black holes. When a star passes close to a black hole, the encounter and be devastating. Tidal forces stretch it, and in many cases, the star is torn apart. But sometimes, against the odds, the star survives. In these grazing encounters, the black hole strips away only part of the star's outer layers. What remains continues orbiting, battered but intact, often left distorted or unstable. Astronomers call these survivors zombie stars because they carry scars of near destruction yet keep shining. Each passage can strip more material, gradually feeding the black hole while prolonging the star's agony. These bizarre systems are natural laboratories for are extreme gravity, showing us the razor-thin boundary between survival and annihilation. To imagine a star limping away from a black hole, its light flickering but still alive, is to grasp how finely balanced the cosmic forces of destruction and entrance can be. Black holes can steal entire stars from galaxies. Galaxies are bustling with stars, but sometimes those stars don't stay put. When two galaxies interact, their central black holes can play tug-of-war, seizing stars from one another. In other cases, stars in the outskirts of galaxies can be stripped away during close passes, stolen by the gravitational dominance of the other galaxy's core. Astronomers have even spotted stars wandering between galaxies, likely casualties of such encounters. The result is that black holes, along with their host galaxies, act as cosmic thieves, gathering and redistributing starlight across intergalactic space. This grand-scale theft reminds us that galaxies are not isolated islands, but interacting, evolving structures. The stars we see in the night sky are not forever loyal to their galactic homes. They are subject to the pull of larger forces, shifting allegiance. When gravity demands it, star clusters can sink into galactic centers and feed black holes. Galaxies are not static. They evolve, and gravity constantly rearranges their structures. Then star clusters orbiting near galactic centers can slowly spiral inward over billions of years. As they fall, their stars are torn apart or absorbed into the central black hole. In this way, black holes grow by consuming not just individual stars, but entire clusters. Observations suggest that some supermassive black holes owe much of their mass to these slow, steady feasts. The process also explains why the cores of galaxies are often rich with ancient stars. Survivors of these migrations. To picture a whole cluster sinking into darkness is to see how galaxies recycle themselves with black holes as engines of transformation. Though destructive, the process helps shape the balance between light and shadow at the hearts of galaxies. Stars can be shredded into streams of gas. When a star ventures too close to a black hole, it can be torn apart in a tidal disruption event. Instead of being swallowed all at once, the star's matter is stretched and pulled into a long, flowing stream. This stream orbits the black hole, gradually spiraling inward, forming a disk of gas heated to millions of degrees. The process shines so brightly that it can outshine the host galaxy for months or years. From Earth, these events appear as sudden, powerful flares, cosmic beacons marking destruction on the grandest scale. Each shredded star is a reminder that even as vast as they are, can be unraveled thread by gravity. These ghostly stellar streams arc across the void like ribbons, beautiful and tragic traces of stars undone. Even black holes can influence how stars form. Though black holes are often thought of only as destroyers, they can also help create as material falls into them. Some black holes unleash powerful jets of energy that blast outward across their galaxies. These jets compress clouds of gas, sometimes triggering the collapse needed to form new stars. In this way, black holes act as both destroyers and midwives of creation, regulating the pace of stellar birth. Observations of galaxies show regions where star formation is unusually active, often linked to black hole activity. The influence of a black hole can extend tens of thousands of light years, shaping the life cycles of stars far beyond its immediate reach. It's a striking paradox. The darkest objects in the universe can play a vital role in spreading new light. Some stars are locked in long-distance dense orbits around black holes. Not every star near a black hole is doomed. Some find stable orbits circling at great distances, held fast by gravity but far enough to avoid destruction. In our own galaxy, astronomers have tracked stars like S2 and S470 orbiting Sagittarius *, the supermassive black hole at the Milky Way's center. These stars move at incredible speeds, some faster than 7,000 kilometers per second, tracing elegant ellipses that confirm Einstein's theory of relativity. To witness their orbits is to watch gravity in its purest form, stars dancing around a void of infinite pull. Though they live in perilous neighborhoods, they endure their paths written by the deepest wells of space-time. They remind us that not every star near a black hole ends in tragedy. Some live out their lives as close companions to cosmic darkness. Stars can form disks that give birth to planets. When stars are young, they are often surrounded by swirling disks of gas and dust. Within these disks, material clumps together, colliding and sticking to form the seeds of planets. Over millions of years, entire planetary systems emerge sculpted by gravity and the influence of the central star. Astronomers have captured images of such disks with dark gaps carved by forming planets, proving that we are watching creation in AC. Our own solar system began in just such a disk about 4.5 billion years ago. Stars and planets are born together, their fates intertwined from the very beginning. To study these disks is to glimpse the origins of worlds, a reminder that the planets we walk on and the moons that circle them are natural outgrowths of the process that makes stars shine. Massive stars can sculpt bubbles in the interstellar medium. The most massive stars pour out so much radiation and stellar wind that they carve cavities in the gas and dust around them. These bubbles can stretch dozens of light years across, glowing with ionized gas at their edges. Inside, the powerful radiation clears away material, leaving a hollowed region around the star. When multiple massive stars form together, their bubbles can merge, creating vast superbubbles that reshape entire regions of a galaxy. These structures are not just beautiful, they influence the next generation of star formation by compressing gas at their edges. From Earth, we see them as glowing shells and nebulae, cosmic balloons inflated by the breath of giants. They show how stars do not simply exist within their galaxies, but actively scoop up them, leaving signatures of their power etched across space. Some stars flicker because of dust in their surroundings. When astronomers see a star's light dim and brighten unpredictably, it doesn't always mean the star itself is changing. Sometimes the cause is dust orbiting nearby, briefly blocking the light as it passes in front. One famous example is Tabby's star, which baffled astronomers with its irregular dimming. The explanation may lie in clouds of dust or debris drifting around it. These flickers remind us that the universe is not an empty stage, but filled with material that can obscure, scatter, or filter starlight. For distant observers, our own sun might flicker the same way if seen through the dusty plane of the solar system. Such stars teach us humility as sky watchers. What we see is always shaped by the space between us and the light. The brightest stars can sculpt entire nebulas with radiation. Hot, massive stars radiate such intense ultraviolet light that they ionize vast regions of surrounding gas, making the entire nebulae glow. The Orion Nebula, for instance, shines because a cluster of young, massive stars at its heart floods the region with energy. Their radiation pushes back the gas, carving cavities and shaping the delicate filaments of light and shadow we see in telescope images. Over time, this fierce energy disperses the very material from which the stars themselves were born, halting further star formation in their immediate neighborhood. In this way, stars are both creators and destroyers, igniting their nurseries even as they burn them away. These radiant sculptures remind us that light itself has force, shaping the architecture of galaxies on scales that stretch across hundreds of light-years. Some stars wander alone through the cosmic void. Most stars live in galaxies bound together by gravity in vast families. But not all stay put. Some stars are flung out by violent events, such as close encounters with black holes or collisions between galaxies. These rogue stars drift alone in the intergalactic void, far from any home, traveling at hundreds of kilometers They may spend billions of years in isolation. Their light crosses unfathomable distances without ever touching another star system. Though lonely, they serve as cosmic messengers, carrying clues about the forces that expelled them. The idea of a single sun wandering through the emptiness between galaxies is haunting, a reminder that even stars can be exiled, glowing defiantly against the vast silence of space. Stars are constantly creating the elements inside you. The atoms in your body were forged long before you were born. Deep in the hearts of stars, iron transforms hydrogen into helium, then helium into heavier elements like carbon, oxygen, and nitrogen. Massive stars take the process further, building silicon, iron, and beyond. They die. They scatter these elements into space, enriching future generations of stars and planets. Every breath of oxygen you take, every molecule of carbon in your cells, every trace of iron in your blood, all were once starlight. Stars are alchemists on a cosmic scale, transmuting simple gas into the building blocks of life. To look at the night sky is to see your own origin story written in glowing furnaces billions of kilos away. We are quite literally the dust of stars carried forward into consciousness. Stars are nuclear fusion reactors in space. At their core, ours are giant fusion engines. Gravity squeezes hydrogen atoms so tightly that they fuse into helium, releasing energy in the form of light and heat. This process, nuclear fusion, is the same reaction scientists hope to replicate on Earth as a nearly limitless energy source. The balance between gravity pulling inward and fusion pushing outward keeps a star stable for billions of years. Without fusion, stars would collapse under their own weight. With it, they shine across unimaginable distances, powering the growth of galaxies and giving life to planets. When you see a star twinkling, you're witnessing the direct glow of fusion, atoms merging in a steady blaze that turns the raw material of the universe into brilliance. Stars are proof that the cosmos itself is a kind of laboratory, running on reactions that sustain all we know. Fusion in stars transforms hydrogen into helium. Hydrogen, the simplest and most abundant element in the universe, is the raw fuel of stars. In stellar cores, pressures are so immense that hydrogen atoms collide and fuse into helium, releasing bursts of energy with every reaction. This is the fundamental process that makes stars shine. Over our time, the buildup of helium changes a star's balance, eventually leading it to expand, contract, or transform into new phases of stellar life. In massive stars, fusion can progress beyond helium, creating heavier and heavier elements. But it all begins with hydrogen. Every sunrise is a direct result of this quiet but relentless transformation, a chain of reactions that has burned for our billions of years and will continue far into the future. The universe's light, warmth, and chemistry all trace back to hydrogen being squeezed into helium, one fusion at a time. Future stars will form from the remnants of today's stars. Don't last forever, but their deaths are not the end of the story. When stars explode as supernovae or shed their outer layers, they enrich their surroundings with heavier elements. This gas mixes with the interstellar medium, creating dense clouds. Over time, gravity pulls these clouds together again, sparking the birth of new stars. Every generation of stars carries the heritage of those before, building more complex chemistry with each cycle. Our sun itself was born from the ashes of earlier stars, carrying within it elements forged in ancient explosions. Future stars will one day emerge from the remnants of ours, continuing the chain. It's a cycle of death and renewal that ensures the galaxy never stands still. Stars live, die, and are reborn, stitching time together with their endless transformations. Some stars are born in violent starburst galaxies. Not all galaxies form stars at the same pack. Some call starburst galaxies. Conditions are so extreme that stars are born 100 times faster than in the Milky Way, Collisions between galaxies often trigger these bursts, compressing gas clouds into furious waves of star formation. Entire regions blaze with young, massive stars, their radiation flooding space with energy. These galaxies shine brilliantly in infrared light, betraying the heat of countless new suns. But the frenzy doesn't last long. After a few 100 million years, the gas is used up or blown away and the starburst fades. What remains is a galaxy forever shaped by that brief chaotic episode. To gloat a starburst galaxy is to catch the universe in a moment of breathtaking productivity, a cosmic nursery running at full throttle. Not all stars are born equal. Some start with dozens of suns. Nearby, our sun was likely born in a cluster surrounded by many siblings. For some stars, this crowding is even more intense. In stellar nurseries, dozens or even hundreds of stars can form close together, their gravity tugging and twisting each other's orbits. Some systems end up with multiple suns bound together, while others scatter their siblings over time. Being born in a busy neighborhood means stars can interact dramatically, stealing planets, flinging companions away, or disrupting each other's growth. Yet, these same environments are where the richest chemistry occurs. As shock waves, radiation, and winds mix material, to imagine a star's first moments is to picture not isolation, but a noisy glowing nursery where dozens of suns ignite side by side, competing and cooperating in their earliest days. Some dead stars continue to shine for billions of years. When stars like the sun exhaust their fuel, they collapse into white dwarfs. Though no longer powered by fusion, these stellar remnants remain hot, glowing with stored thermal energy. Over billions of years, they slowly cool, fading ever dimmer. But that time scale is so vast that the universe itself is not yet old enough for any white dwarf to have fully gone dark. Even dead stars continue to shine, their faint glow marking the graves of suns that once blazed brightly. Observing them allows astronomers to measure the ages of star clusters and track the history of the galaxy. To see a white dwarf is to glimpse both an ending and a resistance, a star's afterlife glowing quietly long after its fiery youth has passed. Stars can be found in clusters containing millions of siblings. Some stars are not born in small families, but in enormous clusters. Globular clusters, for example, pack hundreds of thousands to millions of stars into tight spherical swarms. These ancient groups orbit galaxies like satellites, holding together for billions of years. Their stars are among the oldest in the universe, relics of an earlier cosmic era. From within, the night sky would be unimaginably bright, filled with thousands of suns across every horizon. Studying these clusters reveals insights into stellar evolution, galactic history, and the limits of gravitational binding. They are natural laboratories where stars live together in extraordinary density, showing us what stellar communities can look like at their most extreme. To stand on a planet in such a cluster would be to see a sky ablaze with starlight. Some stars are ejected as runaways from exploding clusters. In crowded star clusters, chaos reigns. Stars tug at one another, and when one explodes as a supernova, it can disrupt the gravitational balance dramatically. Sometimes this chaos flings stars outward at tremendous speeds, creating runaway stars that hurtle through the galaxy. These stars can reach hundreds of kilometers per second, tracing lonely paths far from their birthplaces. Astronomers can identify them by their motion, often finding them racing away from clusters or supernovae remnants. Runaway stars tell a story of violent beginnings, of gravitational dice rolls that decided their fate. Though exiled from their crowded homes, they carry with them the memory of explosive origins. Their speed is a lasting testament to all the forces that cast them adrift. Some stars in our galaxy orbit Sagittarius, the black hole at the center. At the heart of the Milky Way lies Sagittarius, a supermassive black hole about 4 million times the mass of the Sun. Incredibly, there are stars that orbit it directly. Astronomers have tracked these stars for decades, watching them complete elongated paths around the invisible giant. One star, S2, comes so close that it whips around the black hole at speeds of over 7,000 kilometers per second. Observing these orbits provides one of the clearest proofs of Einstein's general relativity, as the starlight bends and redshifts in ways predicted by his equations. These stars live in a perilous neighborhood, but they endure, blazing defiantly while circling a void of immense gravity. To watch them is to see cosmic ballet at its most extreme, suns dancing on the very edge of darkness. Black holes can warp the paths of stars around them. Black holes do not just swallow stars, they also bend the space around them. Stars caught nearby often find their paths twisted into strange orbits. Some may slingshot around the black hole at dizzying speeds, while others may spiral inward toward destruction. Even stars at safer distances still feel the curvature of space-time, tracing paths that deviate from Newton's predictions. Observing these motions has given astronomers a natural laboratory to test the limits of physics. In the Milky Way's center, warped stellar orbits reveal the sheer power of Sagittarius asterisk without ever needing to see it directly. For distant galaxies, stars bent into tight swirls confirm the presence of supermassive black holes too faint to observe otherwise. The warping of stars is both a map and a signature, the hidden fingerprint of gravity at its most intense. The nearest star beyond the Sun is still over 4 light-years away. Our Sun feels close and familiar, but the next nearest star lies unimaginably far. Proxima Centauri, part of the Alpha Centauri system, is over 4 light-years from Earth, about 40 trillion kilometers. If a spaceship could travel as fast as the New Horizons probe which left our solar system, the journey would take nearly 80,000 years. Yet in cosmic terms, Proxima is our closest neighbor, and it even hosts at least one planet in its habitable zone. To gaze at the night sky is to realize that even our nearest stellar companion is separated by a gulf so immense that light itself takes years to cross it. This perspective makes the Sun feel both more precious and less ordinary. Just one star among many, but also the one that sustains our fragile existence. The Sun is just one of hundreds of billions of stars in the Milky Way. The Sun may dominate our skies, but it is only one among hundreds of billions of stars within the Milky Way. Each of those stars has its own story, some solitary, some paired, some with planets, some destined for explosive deaths. The sheer number means that for every star we know, there are billions more quietly burning across the galaxy's spiral arms. Many are smaller, red dwarfs burning dimly for trillions of years. Others are giants blazing thousands of times brighter than our Sun. From Earth, we see just a fraction of them, even on the darkest nights. To imagine the Milky Way in full is to picture glowing disk of light so vast that our Sun is a single grain in its sweep. Our star is both ordinary and extraordinary, a common light, yet the one each that makes our world possible. Most of the stars you see at night are in the Milky Way. When you look up on a clear night, nearly every star you see belongs to our own galaxy. They are the nearby reside. It's of the Milky Way, spread across its spiral arms. Only a handful of the brightest points of light, like those in the Andromeda galaxy, come from beyond. Everything else, Orion's belt, the Pleiades, the stars of the Big Dipper, are local. Cosmically speaking, the Milky Way is so dense with stars that when seen from dark skies, it forms a glowing band across the heavens, the combined light of millions of suns. What seems to us like a personal canopy of twinkling lights is in truth the cross-section of a vast rotating disk of stars. To remember this is to feel both humbled and connected. The night sky is not random, but a window into our galactic home. Stars can be torn from their galaxies by gravitational encounters. Galaxies are not static. When they collide or pass close by one another, their gravity pulls and tugs at everything inside them. Stars, once securely bound, can be flung outward into intergalactic space. These rogue stars drift alone, no longer tied to any galaxy, carrying their light across the vast void. Some may have permits with them, orphaned worlds traveling together through emptiness. These stellar exiles can travel for billions of years, never to return to a galactic home. Observations suggest that intergalactic space is not truly empty but scattered with such wandering stars. Each is a reminder that galaxies are living, moving structures, and that the bonds that hold stars together can, under the right circumstances, be broken by the relentless pull of gravity. Stars can leave behind planetary nebulas as cosmic be markers. When stars, like the sun, near the end of their lives, they expand into red giants and shed their outer layers. These layers drift outward into space, forming glowing shells of gas lit by the remaining core. The result is a planetary nebula, a misnamed but beautiful structure that has nothing to do with planets. Instead, these nebulae are cosmic grave markers, glowing tombs that signal the stars passing. They can last tens of thousands of years, painting the sky with delicate shapes and colors before fading into interstellar dust. Famous examples like the Ring Nebula or the Helix Nebula show us the Sun's likely fate billions of years from now. Though they mark endings, planetary nebulae also seed space with new material, ensuring the cycle of creation continues. White dwarfs are the cooling embers of stars. When stars like the Sun die, they collapse into white dwarfs, dense Earth-sized remnants that no longer fuse atoms but still glow with residual heat. They are the smoldering embers of one's living stars, shining faintly for billions of years. A teaspoon of white dwarf matter would weigh tons on Earth, a testament to the crushing pressure that holds them together. Over time, they cool and fade, eventually becoming black dwarfs. Though the universe is not old enough for any to yet exist, white dwarfs are astronomical fossils preserving information about the age and history of the galaxy. To see one is to witness both an ending and a quiet persistence, the last echo of a star that once blazed brightly in the sky. Some stars die quietly, others in explosive cataclysms. Not all stars meet the same fate. Small stars like red dwarfs fade gently, cooling into white dwarfs without much drama. Larger stars, however, often die in violent explosions called supernovae, scattering their outer layers across space in spectacular displays of light and energy. These cataclysms forge and spread heavy elements, seeding galaxies with the ingredients for planets and life. Some of the most massive stars collapse into neutron stars or black holes, leaving behind some of the strangest objects in the universe. The diversity of stellar deaths reflects the diversity of stellar lives, whether quiet or cataclysmic. Every ending is part of the cycle that keeps galaxies evolving. In each case, the death of a star is never just an ending, it is the start of something new. Stars remind us that the universe is always changing. To look at the night sky is to see both permanence and impermanence. Stars seem fixed, their constellations unchanging. Yet over time, stars are born, live, and die, reshaping the tapestry of the heavens. Nebula blossoms where new stars ignite, supernovae flare where old ones collapse. Clusters drift apart, galaxies collide, and rogue stars wander into the void. Even our sun is temporary, destined one day to expand and fade. Stars remind us that the universe is not static, but alive with transformation. Every twinkle is a moment in an ongoing story that stretches across billions of years. To see them is to flood both eternity and flux. The vast soul, a heartbeat of the cosmos, carries us forward in its endless rhythm. Thank you for joining me on this quiet journey among the stars. We've traveled from their fiery births in vast clouds of gas to our long and steady lives to their quiet embers and explosive deaths. Along the way, we found reminders that stars are not just distant points of light, but the architects of everything we know, makers of atoms, the keepers of time, the storytellers of the cosmos. It can be humbling to think that the very blood in your veins, the air in your lungs, the bones in your body, were once forged in the hearts of ancient suns. Stars lived, died, and scattered their ashes so that you could one day exist here, breathing quietly under their glow. Every night the sky is not just a display, but a history of creation written across space. As we leave this story behind, you don't need to hold on to any of the details. You can let them drift away like stardust in tea. Here, what matters is the feeling, the calm vastness, the sense of being small but deeply connected. You are part of this universe, woven from the same fabric as the stars themselves. If you found calm for here, I'd be grateful if you considered liking or subscribing or sharing a thought down in the comments. It helps others discover this channel, one sleepy soul at a time. But for now, there's nothing more you need to do. Just allow your breath to slow down, let your body soften, and feel the weight of the day slip away. The stars will keep burning, the galaxies will keep turning, and you can simply rest. Somewhere out there, a star is shining whose light won't reach Earth for thousands of years. By the time it arrives, you will have dreamed 1,000 dreams, and the world will have turned countless times. The stars remind us that time is vast, but also gentle, a current we can surrender to. So, let yourself drift, carried by that current, into the quiet dark. Sleep peacefully, dream deeply, and know that the same starlight that fills the sky has always been within you. Good night.
Thank you.